Okay, so my name is Kevin Martin. I've done my paper on geothermal energy. Let me explain first a couple of details what it is. So obviously the root word, you can kind of get an idea of what it is. It's basically heat generated from the earth itself, and that happens through a couple of means. Mostly just the way the earth is formed, and then radioactive decay within the earth creates a lot of heat, obviously. So what geothermal energy does is it captures the heat from the earth and turns that into various useful uses. I've kind of structured the presentation kind of how we structured the class a little bit, taking a look at the different categories of uses that a general resource can have. Obviously, if you're generating something off the earth, it's not going to have much of a transportation element. You can't move the earth. You have to kind of move where you're going to draw the resource to where you want to do it. So you can't obviously power cars unless it's for electricity or anything like that. And there's also no ability to really transport geothermal heat. If you try to put in a pipeline or anything like that, for example, comparing it to natural gas or oil, it loses all of its heat and no longer becomes useful. So the two major categories I'm going to focus on are the residential commercial uses and then the electricity generation. This map shows just how little of an impact right now geothermal has in terms of both general resources and then even specifically the renewables. It's a very low percentage, just 0.2% of all U.S. consumption, and generation is only a little bit better. It's 0.4% of all U.S. energy generation is generated through geothermal heat. That breaks down how geothermal heat breaks down by usage is generally categorized by the temperature of the heat source. So if it is 50 degrees or lower, it's considered a low temperature geothermal heating. That is typically used for heating and cooling. As you go down and generate larger amounts of heat, you're able to use more uses. So direct uses or medium temperature usage. Those typically fall within a range of 140 to 300 degree Fahrenheit range. And then most importantly is electricity generation. That requires a very high degree of heat. So temperatures ranging in terms of the geothermal resource needs to be over 300 degrees Fahrenheit. So just again, looking back at the Earth, typically these are obviously way too high in terms of the thousands of miles, but the picture gives a general idea. The deeper you go into the Earth, the more higher temperatures you're able to draw from it. So at the surface, it's going to be a little bit higher, or a little bit lower. So when you're looking at the low temperature resources, those ones in that 50 to 60 degree range, plus or minus, those are going to be right at the surface of the Earth. The further that you go down, the higher temperature heat you're going to be able to generate. So I'm going to start with those surface temperatures, and that's general uses heating and cooling. So this is actually what drew me to geothermal energy, because it's something that is very practical to any of us. If you're building a home or if you have a home, it's something that you can't just install. It's one of the few resources that you can actually use on site at your house. So the way it works is you get a geothermal heat pump. That typically goes in your basement. When you're installing the technology, you have piping, you drill holes and have piping underground, and that is able to harness the natural heat of the earth. You'll notice those low temperature ranges, typically within about 10 feet below the surface, the temperature of the earth is stable no matter what season it is. So it might be 20 degrees outside, but it's going to be 50 to 60 degrees with the ground about 10 feet down. And in the summer, when it's 80 degrees outside, it's also going to be 50 to 60 degrees about 10 feet down in the earth. So if you lay piping down below, you're able to harness that stable temperature and both draw heat from it in the winter to be able to heat your house, and then also extract the heat from your house and draw the cool energy from the earth in the summer to be able to cool your house. So that kind of started my process. I thought that might be something I want to do in the future is take a look at this type of technology, see if it's something that's going to be practical. My second question when I came with that is if the earth is 50 to 60 degrees in temperature, nobody likes their house at 50 to 60 degrees. People want their house at 70 degrees, or in the summer they want their house a little bit colder. So the second step I looked at is how exactly does the process work? Obviously you're not going to want to draw that specific temperature. And the answer that I found is in how it works is it generally uses 3 loops. There'll be a ground loop, which is what we saw there, basically the loop itself underneath the ground that's drawing that 50 to 60 degree energy from the earth. That circles into the geothermal heat pump, which is inside. That will have a refrigerant loop. The refrigerant loop contains a fluid that has a lower boiling point. So that water that's coming in at 50, 60 degrees, that will be able to actually boil the refrigerant. That will turn into a vapor, and then that's compressed into an even hotter gas. So that's how it reaches the higher temperatures in those cases. That then interacts with the distribution loop. That can be air or water. That will keep that air or water to the comfortable temperatures. You can set it on a thermostat, and typically that interacts with central air, and that will be able to basically ventilate throughout the entire house. So, now with the process, the second step with that is typically the economics of it. One of the inhibitors is it's a very high upfront cost. Obviously, if you're building a house, well, that can kind of be scaled up to a commercial use, but generally if you're doing that, it's going to be an install cost of the geothermal heat pump. You're going to have to actually get those holes drilled, and typically contractors who do this process prefer usage of central air because it interacts well with the system and is able to heat the house. Most of those are actually canceled out by some degrees of savings. The first is tax credits. The Energy Policy Act of 2005 was Congress's initiative to try to give basically tax credits to renewables that originally did not apply to geothermal. That was extended to Geothermal Energy Improvement and Extension Act of 2008. What that does is that any residential user or commercial user who's actually installing this gets to credit 30% for a qualified expenditure. So as long as that is Energy Star classified, then typically you get to claim 30% of the upfront cost or 10% in commercial cases. In Maine, Efficiency Maine actually offers an additional $5,000 rebate. So effectively how this works is Efficiency Maine does provide like an estimate, say it's $40,000 to install a heat pump. So that's your initial high upfront cost, so that can obviously be an inhibitor to people. But if you apply the 30% tax credit, and then again the 5% rebate, all of a sudden the cost goes down to $23,000. So it cuts it almost in half if you're doing that type of process. The second savings and economic aspect of this is the efficiency savings. It's obviously more efficient, both because it's drawing heat from the earth. You're not paying for the resource like oil or natural gas. And a lot of times that 50 to 60 degrees doesn't need to go as high in temperature, so that the electricity resource generating from the geothermal heat pump is a lot lower. So you do need to use electricity to run the pump, but it's typically very, very low, especially for the amount of heat it generates. And that's estimated to have a payback period of only 7 to 8 years, and that's with some decently efficient systems. If you're using, for example, electric heat, that can be cut down to like 3 to 4 years. Additional benefits from it, if you're doing it for a residential, is stable energy bills. Fluctuations in natural gas or oil will have different prices, so you're paying different prices. You can lock them down, but still it's going to have some fluctuation in the price. The energy bills for geothermal is a very low set rate, so you're just paying for that, basically the electricity rate for the pump, and after that everything is going to be a stable cost. So based on the efficiency, you're going to be paying pretty much the exact same amount. Just about every month. It goes up a little bit more or less depending on the temperature, but it's obviously not, if you're heating a house with in really frigid temperatures, it's going to be far more expensive than with geothermal heat. So the more extreme the temperatures get, the more efficient it gets. It's also very low maintenance costs. It's just one device. The pipes generally last 50 years. It's typically very reliable, and it's easy to actually get maintained. And the last aspect, which gets forgotten in that $23,000 estimate, is if you're actually building a house, this would be replacing, for example, if you were getting a furnace installed, that's going to have its own set of costs. So you actually need to factor that in, so it is a little bit less in terms of your high upfront costs, and also it can also replace hot water. You can get it installed such that your water also generates from that, so the heating for the water will be able to get replaced by that. So that's basically the residential aspect of it, what you could see in the house. And actually, this applies to Maine. This applies pretty much everywhere. There are some buildings around this area. There's quite a few contractors who install geothermal resources in houses and commercial buildings, hotels, motels, etc. So with the next set is obviously if you're going to be using those direct usage and high electricity usage, which I mentioned earlier, those require higher degree of heats, which logically you need to get a little bit deeper into the earth to get those. That 50 to 60 degrees is 10 feet down. If you want to go down to 140 degrees and upwards towards 300 degrees, you need to go a little bit deeper. This kind of demonstrates dichotomy between those two resources is on the right is you have the geothermal heat pumps. Those are universally applicable in the United States. So you can do that pretty much anywhere. The one limitation is typically space. If you don't have space to have coil pumps go out into your yard horizontally or into a pond or vertically, it becomes difficult to install those. Also, if the geology of your land area is not conducive to it, that can be an obstacle. But otherwise, comparatively to the direct usage in the power plants, those typically have specific geological regions of the United States that are available to those technologies. And basically that is relying upon where you can draw that heat from. And you might not be able to necessarily tell the geological makeup of the western United States, but if you look at the worldview of where geothermal usages are more popular, it's pretty clear kind of what type of resource it is and what's involved with generating that higher heat. So you can see the most popular areas and most popular countries where geothermal heat is used is all around basically the Ring of Fire and in Europe areas. So basically tectonically active fault lines where the heat is closer to the surface and more accessible. So you'll see volcanoes there, you'll also see the hot geothermal resource. So the 140 degree to 300 range and 300 range above are typically accessed through geothermal reservoirs, and those, through the fault lines, rainwater is able to seep in. The hot rock is a little bit closer to the surface tectonically, and that creates extremely hot areas of heat. Hot water and steam can get trapped into the earth. Those are the resources that are 140 degrees to 300 degrees and 300 degrees and above. So those are actually, if you're going to be using those direct resources, that's what needs to be tapped into. So I'm going to start with direct usages. That's most commonly known. It's a little bit blurry there, but it's a hot spring. So we've been using direct use resources of geothermal heat since ancient times. Roman baths and hot springs in China and Rome, those date back quite a few years in terms of recreational use. And essentially you're able to tap that water. So if you're using that water for another resource, you're using it as a direct use. There's a couple of examples of that. The biggest is this district heating and spacing. So this is essentially kind of a ramped up version of the residential service. You're tapping into a hotter resource and then using that to heat an entire district. So sometimes it'll be a school, sometimes it'll be sections of the town. We'll have kind of a consolidated effort to be able to use that geothermal resource for their heating. This is an example of the greenhouse and aquaculture facilities. So you can tap the water and essentially use it to the heated water to grow certain crops that are more conducive to those conditions. There are some kind of amusing examples I was able to find just in terms of you can use it to raise fish, or you raise different aquatic animals that require higher temperatures in regions of the country where they typically wouldn't be. There's a funny picture I didn't include of a pool in Idaho which they use to raise alligators. And you have snow up in the mountains and it looks like tundra, yet the pool is warm and they're raising alligators in it. You can also use it for commercial purposes because it's somewhat harder, so obviously you can ramp it up a little bit. So food dehydration, gold mining, tanneries, they typically use hotter resources and are able to pump that right in. And that typically used three components. It was a little bit difficult to see in that picture for the district heating, but there's typically a production facility. That's the well itself, so you're drawing from that geothermal resource to bring hot water to the surface. There's a mechanical system which basically exchanges the heat into the loop itself, kind of like with a residential service, that exchange of heat that's then distributed to the rest of the actual district. And the last and most important is power generation electricity. So this is a picture of the geysers. That's the largest and still like the first geothermal energy facility out in California. It's about 70 miles away from San Francisco. It's a 22 power plant geothermal resource field, so it's a very large scale project in comparison to some of the others. And that is an example of the first three types of power plants. So this is the dry steam power plants. That essentially just takes steam out of the earth. So the resource itself underneath the ground is steam, and that goes into the turbine to power the generator and creates the electricity. That's the rarest of the three types because steam is a very rare resource. Typically, when you're finding a geothermal resource, it's going to exist as water under the earth. But for this example, there's also a power plant in Italy that does the same process. they're actually tapping into steam, which is the hottest group of the water. It's obviously hotter temperatures, so you're able to access it and generate more power from it. So that's the rarest and pretty much the most powerful of the three types. A modified example of that is the flash steam power plant. So you'll see a lot of these commonly in like Japan. And that just draws hot water and uses a flash tank to get the steam. That will turn into the turbine to create the electricity and then condenses the steam back into the ground. The third example, and probably the best version of this, is the binary cycle power plant. And this takes the water in its own loop. I'm not sure if it's too low, but it has its own loop of hot water and cold water. That has the heat exchanger, which heats up the binary liquid, which is very similar to the refrigerant in the residential example. And then that goes through the turbine into the generator for the electricity. The key with that binary liquid and the binary cycle is two things. It operates at a little bit lower temperatures. You don't need to draw quite as hot of heat, so you don't necessarily need the steam resource. You can get a little bit lower temperature water from underneath the earth, which opens up different geological regions in terms of availability. And the second is non-consumptive use, which is extremely important. I'm going to discuss that a little bit later when I get to the legal consequences of geothermal heat, but the non-consumptive element is very important for water rights, which we discussed a couple of classes ago. So, going back to our map here, we'll see that there's certain geological regions. That's out west. This will be the higher temperature regions, so California, it's right around here, which is where the geysers is. You can see that spot. But typically that's limited to where geothermal potential is. There's only like 10 states that are able to do this based upon those technologies, which gets us to kind of the cutting edge aspect of geothermal energy, which is enhanced geothermal systems. So, enhanced geothermal systems tries to expand that territory by adopting techniques from oil and gas extraction. So think fracking. It's essentially the same thing without the toxic mystery fluid. It essentially uses high pressure water, and that will expand fissures and can do one of two things. So you either can enhance the existing reservoirs that have water, it can make them more efficient in terms of the water's ability to flow and generate heat, or it could even create them in what's called hot dry rock. It's in Europe. EGS is actually called hot dry rock technology because it's taking where there isn't a reservoir, generating a reservoir, and then pumping water into it via two things. So it's essentially taking that hot, dry rock, and instead of tapping into a hydrothermal reservoir or like a hot steam water pocket, it's creating it and pumping the water into it. This greatly expands some of the potential for it. You'll see all these black dots are the actual sites as they currently exist. And it's a little bit difficult to tell, but based upon the potential with EGS, you see some regions of Texas, Louisiana, Arkansas open up, and a lot more into the Midwest, and even small pockets of Maine, New Hampshire open up in terms of some feasibility for this type of technology. What I had read on that is high granite states typically have regions where it might be more accessible under the EGS since there's more heat there. So, you'll notice, again, I've been kind of pointing towards it the entire presentation, but everything's out west. That's one of the reasons. EGS is trying to expand the ability to create more areas and more potential for geothermal energy, which would allow that 0.4% of generation to expand. MIT did a very advanced study, this was back in 2006, trying to estimate or forecast the potential of geothermal energy going forward. And what they determined is that they're using EGS, there's enough geothermal resources in the United States and accessible to probably power the country until 2050. Really, the inhibitors are the cost of it. One estimate was just a 4.5 megawatt facility or a drilling well that would generate 4.5 megawatts of power in Nevada cost about $10 million to do. And that has a 20% failure rate. So there's some high risk reward in terms of some of this, and a lot of what it suggested was there needs to be some sort of government help in terms of exploration of these sites and locating and identifying these sites that are most available for it. That way some of these companies can avoid some of the exploration fees itself, and then helping with the investment or creating policies that give them more preferential tax treatment or different grants to be able to them to be able to draw geothermal energy as a potential resource. The second inhibitor, which is kind of making a lot of development companies skeptical about the technology, is how we handle water rights. So we touched on this a little bit a couple of classes ago with the two systems, one riparian, which basically is reasonable use of it, a lot of more eastern states where there's no water shortages, in comparison to the western states, which follows the prior appropriation approach. And those, again, it's that first in time, first in right, and you have to actually claim the water that's government owned for beneficial use, and then once you've actually established that beneficial use, you attain vested rights into that amount. So obviously, as I pointed out, there's a lot of steam resources, there's a lot of resources under the ground, so the relationships between geothermal and water rights are intertwined because the water is the resource, but it's also not the resource. They're looking for the heat, but they're also using the water potentially. So a lot of states have to determine how they want to deal with that problem. And that has come up with one of three stances. There's states that have no exemptions or very limited exemptions, including Utah, Wyoming, and Colorado. Utah's kind of a weird example because they have a lot of geothermal resources within their state. So despite the fact that they kind of have terrible policies for it, they still have lots of decent amount of geothermal. The second is temperature-based exemptions. New Mexico, Oregon, and Idaho follow those approaches, and then as we saw with the geysers and a lot of the spots, Nevada and California are by far our most active geothermal states in terms of what they use it for. So I'll discuss those each in turn a little bit. The no exception approach typically treats the geothermal resource as a water resource, so and there's very little room for exceptions, so they would be subject to prior appropriation, which obviously they need to get the rights to that water, which is at times difficult and more expensive. They'll usually recognize it as a beneficial use with some conditions around that. For example, Utah requires the developer to actually go in and identify the nature of the resource, how much they're going to be extracting, how much they might be losing in the consumptive use, to a very high level of detail, which makes it a very difficult prospect to assess when you haven't drilled yet. You're not sure necessarily what's down there, what's there, and what's going to be economic for you. And then there's additional waivers in terms of around some of the conditions to it. So Wyoming has a waiver for public interest to kind of those conditions. So a lot of the conditions to the permit being able to describe what it is. Sometimes you can get a lesser standard there in Wyoming if it's in the public interest. Colorado has this weird outlier type of use where it's exempted for non-consumptive use in the statute, but the implementation regulations, which are what the state engineer follows in assessing, he has discretion to use these. What he follows doesn't actually mention it at all, so when he uses his discretion, he doesn't actually grant these exceptions. The second approach is temperature-based exemptions. What those typically mean is hot water is treated as mineral right rather than as a water right. So in New Mexico, fluid over 250 degrees is considered mineral, therefore it's not subject to prior appropriation. Oregon is similar, uses 250 degrees, however, they also use a balancing process, which water that conflicts between the appropriated water and the geothermal well, have a state official do a balancing process and determine what is the most beneficial use. And then Idaho uses its sui generis approach to separate it from both. It classifies it as a heat resource, and then that heat resource is determined by whether it's above 212 degrees. So looking at more favorable approaches is typically overlaps with it being a mineral right. Nevada and California follow this approach. So this is a map mapping all of the geothermal energy. So you'll notice California up here in the red, that's geothermal. Nevada, but just a little bit. So you can kind of see a little bit in terms of renewables where geothermal stands. It's still not a lot, and when it is, it's isolated into one or two states. Utah and Hawaii will have little bits as well. So Nevada is that second state. So in comparison to California, it might not seem that much, but in comparison to others, it definitely is. But that geothermal right belongs to the owner of the property unless it's been previously separated as a mineral right. So somebody could have prior sold it or reserved it, in which case they wouldn't get those geothermal rights. But usually that will belong to the owner of real property as long as that's a binary non-consumptive system. So if we think about the water rights, one of their prior concerns is with irrigation and such. that water is getting consumed, whereas in a geothermal system, especially if it's binary, it's just continuing to loop back and forth into that resource, so it's extracting and then re-injecting all of that exact same water. So if it's non-consumptive, really it shouldn't fall into the appropriation rights, because it's not actually consuming that water, it's just continuing to cycle it. So that's kind of Nevada's approach. They give it that favorable exemption. So that binary non-consumptive system is similar to what Colorado has, but Colorado's is completely discretionary, and the official doesn't actually, the engineer doesn't actually grant that exception. In Nevada, it's statutorily mandatory, so as long as it's binary, it's going to be exempted from prior appropriation. And the last state is California. California generates 4.5% of its electricity from geothermal, so it's by far the leader, and it also pretty much, their generation itself pretty much dwarfs every other state combined, which kind of puts it as a leader. If it was a country, it would also be the leader, based upon, because the United States is actually the leader in geothermal energy production at this point as well. And that is based on case law, so they kind of use that same approach as Nevada, but it gets through it through case law. So in Periani, they separate it, so I'll just quickly quote essentially what they held in that. And it said that the fluid component of the resource, including the steam, is distinctly separate and different from, it is in fact not water. So therefore, that case pretty much held that it's not water, it's different. And then geothermal kinetics essentially had the same holding there, but with more emphasis on the geothermal water versus the geologic basis of the area. And then, let's see, so how do we reform? So how do we create the ability to allow more states to be like California and Nevada? And one of the approaches which is suggested by a Colorado professor is combining Idaho and Nevada's methods, so basically taking the two major exemptions and making them universally applicable. So exempting non-consumptive or non-diversionary uses. So if you're not diverting the water, if you're not consuming the water, if it's staying in that binary cycle, it should be exempt from prior appropriation. And then again, if it's over 212 degrees Fahrenheit, which is being pulled from that Idaho statute, that would also be exempt. And that kind of makes sense if you think about it as irrigation or farming. Who's using this water, and who would possibly be using that water if it's over 212 degrees Fahrenheit? You can't use that to water crops. You can't use that for general home use typically. So that it's trying to exempt those resources, that hot steam pockets, those extremely hot water pockets, to what uses are most beneficial. The other option, which was suggested, is kind of taking a federally reserved water rights approach. So using like a logic leap, basically. Taking the Geothermal Steam Act, which created the leasing structure for geothermal resources, and combining it with the Homestead Act. And the Homestead Act kind of separated into, for settlers, it reserved mineral rights to the United States when they settled. And under United States versus Union Oil Co., geothermal rights were expressly reserved under the Homestead Act, according to the 9th and 10th Circuits. So essentially, it would retroactively take that Geothermal Steam Act, which acquires developmental rights from federal lands, and uses that Homestead Act to say that those geothermal resources were reserved by the federal government, so they have the ability to do so. So it's kind of combining all of the different constitutional doctrines we looked at, the interstate commerce, the property law, and then again the supremacy clause, because once they have the rights to those, they would, the state laws, those state enacted prior appropriation laws would no longer be in effect. So I'm going to quickly tap on, because I've got probably 5 minutes or so, but quickly tap on a few other legal concerns. The biggest is that federal lands, 90% of geothermal resources are located out west and located on federal lands. So the way that the government approached that was that Geothermal Steam Act, which was later amended by the Energy Policy Act. So that provides releases issued by the Bureau of Land Management into those particular regions. Ownership is retained as a federal mineral state, which allows for a royalty system. The biggest thing with the Energy Policy Act was to decrease those royalties to try to encourage geothermal development in those states. And lastly, it allows for cooperative agreements. So if we think about our diagrams earlier with oil resources, with multiple people tapping into one well from multiple sides, that's essentially what this does for geothermal. It allows the government to require cooperative agreements between two holders of a common reservoir to make sure they don't drain the resource. A couple others is everything about geothermal needs to be permitted, so there's going to be exploration permits, drilling permits, facility construction utilization permits, commercial use permits, and that extends all the way down the ideal scale to the residential usage. So if you're doing this at your house, your contractor is going to need to follow all of the local and state ordinances for geothermal permitting. It's also subject to all of the environmental regulations, a lot of the ones that we touched, all of the NEPA, so they would have to typically do an environmental assessment, and if there's a finding of significant impact, they would have to go through the entire process of an environmental impact statement, which can be costly, so again, it's another inhibitor in most cases to that, and that's also subject to states like California, which will have very involved state mini NEPAs. They're also going to have to fall under those qualifications as well. So, are there any questions?
The Nevada locations there seem awfully close to the Yucca Mountain nuclear waste repository site. Did you run into any, can these two uses be comfortably consistent with each other?
I didn't run into any specific articles regarding the two being conflicting in any way. I think it's mostly just, there's very little environmental impact from geothermal. I mean, obviously things can be contaminated and such, but if Yucca Mountain has a problem, the whole area is going to have a problem, would be my answer to that, so it's not going to matter. I think in terms of geothermal, their reaction is just going to be steam. There's not going to be any sort of disasters or anything with that. It's just tapping into that. So I think to the extent that there might be any problems with Yucca Mountain that might inhibit the population base, that might eliminate the need for it, as an example, but as long as that population base would be there, it would be good for the electricity purpose.
As far as home systems, has there been any appreciable decline in the price of systems from when they first came out to now, or is it sort of been static where they've always been?
I don't have any price estimates over time for geothermal heat pumps. I would assume as technology continues to increase, it's going to continue to go down. Additionally, there's like probably 12, 13 contractors in the state of Maine just by itself that do this. So again, it's just going to be the market approach. As there's competition to it, it's going to continue to go down. And as they get more efficient doing it, it's going to continue to go down. But I think it's also going to be tied to, demand for it. Right now, I think there's over 1 million units across the United States, but I think they're selling over about 100,000 units a year. So it's continuing to go up and up. So obviously, I think as more people demand it, that price is probably going to continue to get more efficient. More competitors get into the market. It's going to take care of it. So.
Is the potential for geothermal in Maine really a residential potential more than a commercial potential?
Yeah, for the most part. I think based upon like the map itself, it's not going to, unless the enhanced geothermal system, which is kind of on its first leg of expansion here, so that's not going to bring, I don't think, a geothermal power plant to Maine anytime soon. I think it might, as a better resource, it might be something like direct usages. So we might have alligator farms in Maine, or we might have more efficient greenhouses that are able to tap into some of those resources potentially. I think the advantages that Maine and states would have would be that riparian approach. So if we're drawing water from it, which we probably would need to do, because it's going to require geothermal, enhanced geothermal, so we wouldn't have a hot water reservoir. We'd be able to pump in what specific water. We'd have to draw water from the river to enter into the system injected. So to a certain extent it's possible. I think it's going to be in those mountain regions where you can access the granite, but I think it's going to be, it already is from a residential stance, just like everything else in the United States. So Maine is available. We do have multiple contractors that would do it. So pretty much the residential aspect of it is already there. The commercial aspect would be that area that depends upon the technology from enhanced geothermal systems.
Just, I guess, a comment that maybe will address some of those other questions about residential use. I retrofit my house for a ground source heat pump last fall.
Mhm.
And the vast majority of the cost is drilling the well. The vast majority, 2/3 to 3/4 of the cost is drilling the well. But even so, depending on variables like the electricity rate and whatever you're replacing, we actually our payback period, you had 7 to 8 years up there, but ours was 0. The cost to finance on a decent home equity loan plus the cost to operate is less than we were spending on oil and wood before.
That was one of the studies that I looked at as well. Is if you're financing it, essentially what the argument was is if you're financing it or if you're tapping it onto your mortgage, you're adding something like $30 to your mortgage by financing it through the mortgage, and you're already paying that back through the efficiency it's generating. So that's part of the argument. And again, a lot of it's like it is the drilling. So that's your major upfront cost, and depending upon the method, I'm not sure. As an example, I don't have studies based upon which method is more cheap. Did you use vertical wells or did you use
Vertical.
the vertical? Yeah, so there's vertical wells which draw directly in depending on the plan, but I think it might actually be more cheaper if you do like the horizontal, depending on where you are and how much room you have. That can take some of the cost, but again, it's all the drilling. The pumps themselves are probably on par with a typical, like, I'm not sure compared to a water heater or anything, but it's basically a unit like that. So it's not typically that expensive. It is the drilling and what else that will do it.
And I can give you a number anyway, but the unit itself is basically a refrigerator.
Right.
And it costs 1/3 to 1/2 as much as a new furnace, basically. But then it lasts twice as long and requires no maintenance at that time. So
And what's the comfort comparison, just of how much you're enjoying the,
it's a lot more even.
yeah,
If you've sized it right, then essentially in the cold months, the device runs continuously, more or less, and the temperature stays constant. Whereas we used to heat with wood, and we would stock up the
yeah.
heater at night, and we'd get to 78 in the bedroom, and then by morning it was 50 in the house.
Yeah.
Do you have like a central air system that does? Yeah. I think a lot of that, I mean, it's more of an incidental effect, but a lot of times when you do these systems, they install it via central air, and central air is just a better distributed system into it. But another thing, a lot is the cooling aspect. I think they've said that it can be, I think the one that, I'm not sure if you've noticed, they said it can be a little bit more humid, or there might be humidity concerns with it. I'm not sure if that's accurate or not, but that was one of the concerns I ran into with the. Maybe not. Any other questions?
Some of us like that. Has this gotten caught up in the legislative bill with efficiency main of, oops, we forgot to put in the comma or the and or whatever?
I haven't noticed anything specific for that. The only efficiency main element that I really closely looked into, I might go into this a little bit more
Yeah.
in my paper. It was kind of a time concern for the presentation, but was the rebate aspect of it. So kind of the general, we're trying to encourage the policy element of it, but
Yeah.
not much more than that. I think in terms of the commas and crossing T's element of it is more that that 2008 Act, which amended it, that had a lot of weird elements to it. I was looking at it this morning, some additional things, and like that act was the one that changed daylight savings time. So it had like weird, crazy elements. That 2008 we changed the daylight savings time a week. That's where it was, and but there were other elements that they dropped. There was Kyoto protocols in there that were originally drafted that got dropped. So it was a large geothermal, or a large environment, basically energy-related bill that had a tiny section of it on geothermal, which is basically what was covered here.
Thank you. Good job.
thought about assigning it as like a precursor to my presentation. Everybody has to watch that PBS film From Stump to Ship. Have you ever seen that? It's great. Basically cover my whole presentation. You stole my password. Yeah, so we're going to talk about biomass and biomass to energy, stump to consumption, and this is kind of the format of how we're going to cover it. Start off by just talking about in general what biomass is, how it's produced, how it's harvested, and how they pull energy out of it. How you guys can take advantage of that. So, what is biomass? Essentially, biomass is any organic material that through photosynthesis has stored energy within its fibers. Over time, humans have used it, fires in your kitchen, cooking and heating type stuff. But now we can harness that energy as more of a commercial power source. And that's kind of been a development over the past 30 years, and that's a lot of what this presentation is going to talk about. But first, what we're not going to talk about. So biomass can also be created into a liquid fuel, also usually called biofuels, things like ethanol. This isn't necessarily part of the biomass to energy discussion like we're going to talk about here. This involves a lot of production, a lot of chemical change, so we're going to stick more to the biomass that is, you cut it down, you dry it, and you burn it, and that's your energy. So for our purposes, biomass is animal waste, especially in a lot of the poorer countries in the world. They use dried animal dung as a fuel source. Animal dung obviously has organic material in it that is combustible and makes a decent, but not perfect, fuel source. There's also potential for agricultural crops to be grown for their biomass. Things like hemp, switchgrass, they can be grown every year. Some of these products more than once a year and harvested more than once a year. And through drying and processing, they can be burned as fuel. And then more for Maine specifically, wood. And wood can mean many different things. Obviously, it all starts as a tree, but the process of burning it can involve many different products. We'll get into all of that. First, animal waste is biofuel. It has some positives. It's really cheap. It's obviously renewable. And naturally available in the wider world. That's why it makes a great fuel source for more of the impoverished countries and communities in the world. It's out there. It allows them to take full advantage of the natural resources, both the animals that consume the product, and then they can consume the animals and animal waste. Just needs to be dried, and then it's usable. However, there are significant concerns with using animal waste as a fuel source. Sanitation is a big one. Especially now, a lot of countries are beginning to experiment using human waste as fuel, and there's a lot of sanitation concerns with that, obviously. The Bill and Melinda Gates Foundation has been funding a lot of research on these new toilets, essentially, that require no electricity, but can turn human waste into usable fuel. So it's kind of like one of those next era animal waste products. And then the other issue is indoor air pollution. The World Health Organization has some studies about indoor air pollution from ventless fireplaces in third world countries that essentially says about half of childhood deaths, children under 5 years old across the world, are caused by disease or pneumonia from unventilated kitchen fires. And not only just children are affected, but adults, premature deaths, something like 4 million a year, and over 3 billion people are using this type of fireplace across the world. So it's a pretty big issue, something the World Health Organization has taken a big concern, a big part of in the past few years. And then agricultural crops, hemp, switchgrass, miscanthus. These can be grown in 1 or 2 cycles a year, and hemp especially can be grown in just 90 days. So even in a place like Maine, we could potentially grow 2 crops of hemp in a single growing season. Hemp hemp is not weed. Hemp is hemp, weed, very, very different. Hemp is grown for the material in the stalk, so all the energy goes to producing the fibers in the stalk, which is what you're going to harvest for biomass, whereas marijuana is grown for puts all the energy into the flower. So hemp, high yields, obviously it's very dense. You can grow it just like this. It essentially requires no herbicides or pesticides because it's so dense. Grows 2 cycles a year. Doesn't pull much out of the soil as opposed to like other agricultural crops. And like I said, because of the shading, it doesn't need a lot of herbicide. Once it's harvested, and these things can just take huge tractors, mow it down, as you would see in a cornfield, and dry, they press it into pellets. And when you press it, the dried material into pellets, it can make a really great fuel source, because you can also control the density, which is really important as far as getting a high BTU output of your fuel, is to have a high density. When you press the pellets, you can control that by how much pressure you're putting. And then wood. That's a big tree. We don't see none of that anymore. Wood is obviously the one we rely on the most here in Maine, because we have a pretty substantial natural supply of it. More than 90% of Maine is covered in forests, so there's a fuel source readily available to Maine and Mainers, and it's been harvested by them for hundreds of years, and the Native Americans even harvested it as far back as 10,000 years ago. So. This is a study that was just done by the Dutch government, the government of the Netherlands, called Biomass, Wishes and Limitations. Eventually, I mean, it was really exploring the potential of biomass to replace fossil fuels in the future. The study, like it says, wishes and limitations, it basically comes out that biomass is not the one and sole answer to replacing fossil fuels, but in places like Maine, where it can be a regional solution because we have such prevalent natural resources. So Maine forests. Like I said, Maine is more than 90% covered by forests. And for about 10,000 years, those forests were naturally managed by Native Americans through use of fire to clear the ground, which left a lot of the old growth still standing because it takes a really hot fire to bring down a tree that size. So Maine forests, pre-European conquest, lots of large trees, large pine, and it was sustainably managed. However, when the Europeans came, metal tools, disease, all that stuff, they really took advantage of the Maine forests. Within about 200 years, Maine went from being 92% covered in forests to being about 60% covered in forests, before we kind of turned it back around and figured out how to sustainably manage the woods. Wood can be broken into really 2 categories. 2 broadest categories would be hardwood or softwood. In Maine, we have both. However, a lot of the northern Maine forests are harvested for softwood. Hardwood, however, makes a much better fuel source. It's more dense, has a higher BTU output, but it takes a long time to grow. And especially when you're trying to burn logs like firewood, you need a tree of significant diameter. When you're consuming them as chips, which is what a lot of commercial power plants do, the diameter of the tree doesn't matter quite as much, so you can harvest younger trees, you don't have to wait quite as long. Softwood has a higher moisture content and a lower BTU. And also, when they're burning it, can be a little more corrosive because of all the sap. However, it's lightweight and strong, so it makes a really great timber source. So generally softwood in Maine is used for lumber. However, the milling process produces a byproduct called mill waste, and mill waste is often burned by commercial power plants in Maine. And then firewood, it's not the ideal firewood, but if you own a plot of land and you need to cut firewood for the winter, or you're trying to sell it, you're kind of going to cut whatever's there. So it is used as firewood. This is just an example of how the forestry industry has changed in Maine. So before 1960s, when it was a guy out there with an axe or a saw and maybe a horse or a small skidder, a logger could cut 9 cords a week. Now, with some of the technology changes, you're looking at more like 75 cords a week per logger. And we're not necessarily cutting that much more total cordage. You see 2.9 million in 1950, so we've doubled over 61 years. But the rate we can produce it has gone up almost 8 times. So what that means is less jobs, essentially, less forestry jobs. One guy in a machine like this can now do what 10 guys like that could do. So it's changed the industry. This is kind of how, this is some old school pictures here, show an example of why they were limited to 9 cords a week if you had to cut them down by hand and then haul them using horses. Another thing I kind of want to show is just the size of the lumber here. And then if we look, this is maybe more modern, you look at the size of the trees, much smaller. That's because we're now on like 5th, 6th, 7th generation forests as opposed to original forests those older pictures show. So there are some problems with like the new technologies that allows them to cut so much faster, which encourages clear cutting. And clear cutting has significant environmental concerns. Soil compaction, which leads to water pollution and water sedimentation. Mudslides, not so much in Maine, but especially in West Coast, steep slope areas. And this is some examples of clear cutting and what happens when you clear cut. Water stays on the surface, creates a lot of mud, which makes it basically impossible to harvest. Most Maine forestry takes place during the winter because it's so much easier to transport. Mud is much less of a problem. However, late summer, fall, up north, they also do quite a bit of timber harvesting. The spring, you can't get out there, it's too much mud. So distribution hasn't really changed too much. We've went from animals to motorized vehicles, but you can see the process essentially the same. You're taking it from the woods. Both of these, the truck would drive right into the woods to the woodlot and be loaded up. The same with the horse back in the day. And take it right to wherever the consumer is, whether it's a company burning it for biomass energy, or whether it's Joe and Jane burning it for their firewood in their home. So in Maine we have 2 biomass to energy markets. There's a consumer market, which is essentially your firewood. That's a consumer to consumer market. And then we have the electric utility industry, which is the biomass commercial generation industry. We'll talk about both of those. First, firewood. I'm just going to spend a minute because I think we all know about firewood. So it's a consumer-to-consumer market used typically by rural Mainers for home heating, cooking. Peter's not that rural, but he also burned wood up until last year. So, you know, it's available. It's easily available, easily harvested, and makes a lot of sense, especially in northern Maine when you have power lines that are subject to having trees fall on them and you're losing your power in the middle of the winter, which is the most inconvenient time, obviously, to lose your power. Wood provides a consistent, you don't need a consistent source of heat, you don't need electricity, you just burn it. And firewood generally comes as cord wood, that's like 16 to 24 inch logs. It can come split like this, or full logs if it's smaller stuff. You season it typically, which means you let it dry for a significant period of time. However, it's cheaper to burn green wood, which is fresher cut. There are some regulations about firewood in Maine. Actually, this is substantial. This is one big concern for the Maine Department of Agriculture, and that is invasive species. There's a regulation basically that you can't bring any firewood from out of state or out of country into Maine. Burn it where you buy it. I think this is Daylone's phone number. Anybody? And this is enforced by the Maine Forestry Service. I think it's got to be pretty tough to enforce. I mean, if someone brings firewood in the back of their car from New Hampshire for whatever, but
And no local protectionism at all.
yeah, well, maybe a little bit. However, we have all the forests. It's much easier to cut it here and burn it here than it would be to bring it across as far as an economic standpoint. But, so biomass to energy as a commercial power generation really took off after the 1970s oil crisis and the energy crises. Essentially what happened was oil prices, we talked about this in this class, oil prices were high, supply was low. OPEC put an oil embargo in 1973 on America, and so that really pushed our country to develop a renewable fuel source, or more than one renewable fuel source. In Maine, because we have so much timber, that push led to a electric biomass generation industry. And this is essentially an overview of kind of what happens, the overview of the entire electric utility industry. You first have generation, that's your power plants. They're taking the fuel from the foresters and they're burning it and making electricity out of it. That's being distributed through transmission lines owned by CMP or Emera Maine and supplied by a bunch of different companies at a PUC set rate. We'll talk about that more later. And then consumption, that's the end user, that's us. Could also be businesses. Maine generates about 26% of its overall electricity consumption from biomass, by far the most in the country. The national average is something like 4% from biomass, 6–7% for renewables, depending on where you read your information. So Maine commercial electric generation. This is actually a wood-burning power plant in Maine. It's still operating today. And most of these plants, there's been upwards of 10 of them commissioned and decommissioned over time. Right now, I think there's 8. Most of them were built in the 1980s from momentum gained from the oil crisis in 1970. These were mostly national, but some international corporations that were investing and building these plants. And most of them were built as small, what's called qualified facilities. And at the time, that qualified them for special contract rates that were administered and mandated by the state. These plants got 20-year contracts at a set rate that was equal to what oil was at the time, which was really high. So they were making significantly more than they probably would have if they would have had sell it at market rate. And that was to protect the industry, basically. It was a new industry, and the state didn't want it to collapse immediately when oil prices fell, which is exactly what happened in the 90s. Oil prices fell, and when these contracts went up, a lot of these power plants went out of business. This is an example of essentially how power is generated from biomass. This is the Sherman Wheelabrator plant, which is where I grew up, and my dad worked there. And so we're going to talk about that as more of a hands-on example in a moment. But this picture matches up pretty much with this in the process. So we have the fuel comes in here, that's this belt here, feeds it up into the boiler. Boiler heats the water source. Most power plants were built right on a river or a stream of some sort, which is where they get their water. So it heats a water source. That water source creates steam when it evaporates, turns a turbine, turns a generator, creates electricity. This dust collector is actually an EPA regulation for pulling carbon out of the smoke. So they're regulated, they have to have something like this. This technology changes all the time. There's new requirements. I think the latest ones were in 2006, which basically say if you're a biomass burning plant, your smoke can't be 6% carbon for more than 6 minutes every 2 hours or something like that. And they measure the density, or it's called an opacity regulation. They measure it by shining a laser through the smoke, and when the laser reflects back off of something, they can determine the density. And so this is the truck that hauls the chips, and this is how they unload it. They just put it on this huge ramp and tip it up, and you can see that's what's going on right here. So the chips come out and then up into the boiler. Oops. So the Sherman Wheelabrator. This was opened in 1986, and at its max, it could generate 20 megawatts an hour. It's pretty typical for these plants. Some of them go up to like 40 megawatts an hour. On this, they're talking. So this is the Google Earth view of the power plant, and it was strategically placed where it was. This is the power plant here because this is a mill. This is the Sherman lumber mill. So the power plant would burn the waste from here, which essentially eliminates all of their delivery costs and gives them cheap fuel. So not only did they have favorable long-term contracts at oil rates, but they also had fuel sources. You just had to take a truck from here to there, and that was essentially it. This company, Sherman Lumber, had operated for 70 or 80 years prior to the mill being there, and they had just been dumping their waste in the woods. So Wheelabrator had 70 years of waste to burn through as well. However, they went out of business. Wheelabrator closed in 2003, I think, because they ran out of junk wood that was already stored up. And then I did the zoom outs here so that you can kind of get an idea of what the area is like. This isn't really an economic boom area. We're talking maybe 400 people live along this road here. I know it's tough to see with these pictures, but so this is the lumber company and the mill, and these are houses. And if you zoom out one more time, it's all woods. That's it. This is Mount Katahdin, so we're about 13 miles from Mount Katahdin, and there's not anything in between the two. Yeah, so to have something like this generating max $20 million a year in a community like this with 600-700 people, it was a pretty big deal. Doesn't exist anymore, so there's not a lot of industry left. The Sherman Lumber Company is also closed. This is the actual fuel source they're burning. So they're buying mill waste, which is bark, sawdust from the mills. They're buying hardwood chips. These are directly from the woods. Essentially a chipper, just a mulching machine, drives into the woods. They throw the hardwood in there. Out comes chips. They load it into a truck and they deliver it. And then the power plant mixes the two together. It mixes all of their stuff together so that they have a more consistent fuel source. Because hardwood has a higher BTU, the softwood bark has a lower BTU. By mixing it all together, they get something a lot more consistent. Where did I? This is just a map of where the biomass plants exist in Maine. This is from the EIA website. A lot of these are mixed fuels, so they use hydropower to some extent and biomass power. All of these companies, all of these ones over here are just biomass. But for instance, there's a plant in Westbrook that burns chips, but they also use hydropower. There's a lot of paper mills, not a lot anymore, but a few paper mills who, as a byproduct of producing paper, they also produce electricity. When it goes over the amount that they actually need to run their plant, they sell it back to the grid. And these are just some statistics comparing Maine to the national average. So other renewables, down here at the bottom, that's mostly biomass, but it also now includes wind power, which is ever increasing. And hydroelectric is something separate here, but really you could say that's a renewable, obviously, as well. So in Maine, we have 40% of our power coming from either biomass or wind power, as opposed to the national average, about 6%. So generation electricity, like I mentioned before, is regulated by the EPA, and by the PUC was the agency that was responsible for administering the long-term contracts, the state mandated contracts for these biomass facilities. But the DEP regulations are the ones that really impact the mill itself. They're the people that, when my father was working at the mill, he'd have to be dealing with that agency. They'd be coming to measure the opacity and the CO2 emissions. This is the newest way that our state has made a push for renewable energy, and it's through the creation of a renewable energy certificate market. And basically all the New England states except for Vermont have now put in these renewable portfolio standards. These are statutory state law that set up standards for how much of your electric generation in your state has to be generated from a renewable source. So Maine put this into effect in 1999 under Governor Baldacci, and essentially at that time it said 30% of Maine electricity has to come from a renewable source, which sounds great because even New Hampshire, theirs was 2%. So we were far and away the most restrictive. However, at that time, we were generating 46% of our electricity from renewables. So the demand of the statute was 16% lower than what we were already generating, which, when you have more renewable energy than necessary, these renewable energy certificates are basically valueless in the state. When you generate 1 megawatt of renewable energy, you get 1 renewable energy certificate. And those renewable energy certificates can be sold to other companies to meet their needs as far as meeting the state regulation for 30% renewables. So each company, Amerimain, CMP at the time, when they were buying, their supply had to be 30% made up of renewable resources. And that was never a problem. They never needed to buy these energy certificates to make up the difference. However, in Massachusetts, Connecticut, where they have less renewable resources, that's the market really where Maine companies are trying to sell their certificates. They can get maybe $40, $35 per renewable energy certificate, which is per megawatt, in Massachusetts or Connecticut. If they try to sell it to a Maine company, $8, $9. So the best way for these renewable plants, these biomass plants, to make money is to sell their renewable certificates out of state. And this is a comparison of the renewable portfolio standards among the different states. As you see in Maine, we have 2 classes. Class 2 is like existing renewable resources that existed when the law was passed. So these are plants mostly built in the 1980s and 90s with lower environmental standards. New Class 1, which is a lot of wind power at this time, that was scheduled to increase every year up until 2020, until Maine hits 40% total renewable energy. If you look at the other states, probably hard to read back there. So by 2020, Connecticut is looking at 27% renewable electricity. Massachusetts is looking at 27%. But right now, they're around 20, and Maine is at 39. So distribution of electricity. In Maine, we're connected to a larger regional grid called ISO New England, which is the Independent Service Operators of New England. So we can sell and buy electricity from a larger grid. It creates a more consistent supply. And as we've talked about, a big problem with electricity is the ability to store it. You can't really, or not efficiently. By connecting to a larger grid, we don't really need to. We can always pull from somewhere else. And the grid actually connects to Canada on the other side. They're not part of ISO New England, but we do share power with them as well. And then there's this little section up north. This is current. This is the Northern Maine Independent Service Association. They pull a lot of their power from Canada, and they're not connected to ISO New England. You can see from 2005 to 2014, the area of Northern Maine Independent Service Association has really shrunk because everybody, for the most part, would like to be a part of this regional grid. It's less expensive, less administration, all that stuff. So in Maine, we basically have 2 distribution companies that serve most of the population. That's Amerimain and Central Maine Power. Before FERC demonopolized the utility market, these companies were Bangor Hydro and Central Maine Power, and they did generation, they sold the electricity, and they delivered it. After FERC regulated that, they were no longer generating electricity, they were just selling it and delivering it. In 2008, that changed again. Now these companies are solely own the power lines, so they're your distributors. Your supply comes from another company, and that's determined by a standard offer rate, which is set by the Public Utilities Commission. So when you get your electric bill, you're paying 11, 12, 13 cents a kilowatt hour. 4.5 of that, or somewhere thereabout, which is the standard offer, goes to the supply company. The 6, 7, 8 other cents goes to either Central Maine Power or Emera, basically for use of their power lines. And these are their regions down here at the bottom. So Emera serves most of Washington, Hancock, Penobscot, and some of Aroostook County. This is southern Maine. You can kind of see here. So this is CMP service area as opposed to Amerimain service area. There's a lot of Maine that's not serviced by either of these companies. One, because nobody lives there, and so it's not economical for these companies to try to run their power all the way up there. Those communities generally have a co-op of some sort, a local fuel source, a lot of them probably burn firewood and have less electric demands than communities in southern Maine. And utilities are also regulated by state and federal agencies. PUC, like I said, sets the standard offer rate. Right now, in southern Maine, the standard offer rate is 4.5 cents. That means if you don't choose a supplier, your electricity is supplied at 4.5 cents per kilowatt hour. If you're in northern Maine, it's like 6.5 cents. And I think that's just because less people dispersed over a greater area, higher costs. And then this is just a quick glimpse at the consumers in Maine. There's about 800,000 electricity consumers, 850,000 electricity consumers in Maine, and they're getting about, well, they're over 1,000 gigawatt hours a year. Biomass is producing about 425 of those gigawatts. So it's a really substantial industry in Maine. We're talking, 26, 27, depending on the year, % of our total electricity is generated from biomass. And that's what I got. Any questions?
The part about waste being biomass was really interesting, and I know that I read and had heard a while back about Sweden doing a lot with that, but mostly with human waste.
Yeah.
And I hadn't heard that the Melinda and Bill Gates Foundation had done anything with that. But did you read anything about that, or about
I didn't know
America doing anything?
I haven't heard anything about Sweden, but actually, I say that one of the winners for the Bill and Melinda Gates Foundation, they basically had a competition to encourage people to innovate the new toilet. And one of the winners is called the Omni toilet, and I think it was actually developed in Sweden, which turns human waste into a fuel source of some sort. The other point of this competition from the Bill and Melinda Gates Foundation was not only to make an energy source, but also to pull clean water from waste, to extract the nutrients necessary for maybe growing crops or whatever from the waste, and to do it all sanitarily. So they had many goals, not just fuel sources, but it's interesting. You can read about it. Yeah.
I love 3 of the visuals in there for picking up points we talked about before, and then one, the humorous one, was the sign outside the hemp plant.
Yeah.
Don't come in and raid us for weed, we're using this for other purposes. The second was the burning the human or animal waste in that. And imagine doing that every day of your life in that confined kind of quarters. And God, what sort of health problems do you have? And that's 2 billion-ish people in the world are living with that. And then the third, and this picking up on some of the comments in my introduction lecture that I hope you've had a chance to listen to at this point. Both the humans there with what look like the redwood trees, cutting it with no power saws, and then the horses hauling it. That was Professor Hoffman's comment of this is how the energy world worked substantially in the Middle Ages. You're providing food, and that's what powers the humans and the horses, but they then have to go out and do all this stuff that we've now got wonderful machines.
Yep.
That can make it
I
happen.
say wonderful, but it causes some problems.
No doubt about it, but I suspect if you were to ask any of those people, here's some of the pollution impact, if we could get you a power saw, would you rather have that? I think probably they would have the sense to say, give me the power saw and I'll do my weight workout down at the gym.
Anybody else?
Other questions? Great. Once again, splendid jobs on both of the presentations, and